So I guess we can start.
Thank you. So I'm trying to share my screen. Does it work now?
Yes, sir.
Perfect. Thank you. All right. So thank you so much for inviting me for this very timely workshop. I look very much forward to participate in the upcoming talks. So in my talk, I will be presenting some quite recent work from our laboratory on implementing quantum gates, Gaussian gates, on a photonic platform. So there are many different approaches to quantum computing. There are many different platforms that can be used. So some of them are shown here. Probably the two most leading platforms are the superconducting electronic platform, as well as the trapped ion platform, where super nice results have been demonstrated within the last few years. But there are many other interesting platforms, and the platform that we are considering, we are working on in our laboratory is the photonic platform. So within many of these platforms, you can decide between two different types of encodings, Qubit encoding or Q-mode encoding or bosonic encoding. And have a slide here comparing the two different types of encodings. So this slide was prepared by my PhD student, Jacob Astrup. So the idea, I mean, in order to do quantum error correction encoding with qubits, then you need some redundancy encoding. So you need to encode your logical qubits into numerous physical qubits. So this will require many qubits, many two-level systems, and there's a huge resource overhead. So this is bad. Also, since you have many qubits, every single qubit will have noise. So many qubits will mean a lot of noise. And also, as far as we know, so a reduced error rate has not yet been demonstrated, I mean, experimentally demonstrated in that platform, I mean, using qubit encoding. So the good thing is that if you can scale this up to very large sizes, then the error rate is very, very low, and you can actually achieve a fault tolerance, which of course is a very good thing. In the bosonic approach, here we're encoding a qubit into a harmonic oscillator, into a boson. So, and the nice thing here is that you only require one mode. So, and then you're just making use of many levels in that single harmonic oscillator. If you need larger codes, then you have the same noise channel. You just have one channel, you have one mode. And also using this approach to quantum error correction, an error rate has actually, or a reduced error rate has actually been demonstrated in an experiment. I forgot to put the reference here, but this was demonstrated, I think, 4 years ago by the group in Yale, where they used the cat state encoding. The bad thing is that it's not really fault tolerant, so you will need more than one single mode in order to make it fault tolerant. So this is like a very rough comparison between the two approaches, and this also nicely illustrates why the bosonic approach is becoming more and more popular. The popularity of the bosonic approach can also be seen in this graph here, also prepared by my PhD student, Jacob. So here I'm plotting the number of papers published where GKP encoding is mentioned. Don't look too much at the absolute numbers, because I think we didn't find all papers, but the trend I think we can trust. So and we start with the original proposal by Gottesman, Gitef, and Presko in 2001, and then we see that within the last 3 years it simply took off. So there's a lot of work going into this field. Okay, so what do we have to do in order to build a quantum information processor based on bosons, or continuous variables, as we also used to call it? There are basically 4 different tasks that we need to consider. So first of all, we need to initialize our Q modes or our qubits in the oscillator, and this can, for example, be DKP state, can also be cat codes or other types of bosonic codes. Then we need to be able to perform transformations, gate transformations, and here, of course, we need to perform single mode as well as two mode transformations, and they have to be combined into a circuit. We need to look into upscaling. We need to be able to scale up the platform, and then, of course, at the end of the day, we also need to do some quantum error correction. Otherwise, it will not work, because I mean this approach inherently comprises a noise. I mean, the DQP code always contains noise, so we inevitably will have to correct for that noise. Okay, so a lot of work has been done already. So, for example, DQP states they have now been produced in the microwave regime using superconducting circuits, and also in the vibrational modes of trapped ions. So these are very recent experiments reported in Nature within the last year or so. Very nice work, and also people have also used these platforms to demonstrate the quantum error correction coding or quantum error correction by the same two groups. But this is also done in the microwave regime as well as in the vibrational modes of ions. So in my talk, and what we have been looking into in my group is to look at the two other tasks. I mean, gate transformations and upscaling. And this is actually what this talk is going to be about. We will be looking at how to implement gates and circuits in an optical cluster state, which is scalable. So this will be what I will be talking about for the rest of my presentation. Okay, so what gates do we have to implement? So we have to find a complete set of gates, of course. And the complete set of Gaussian gates comprises the rotation gate, the displacement gate, the squeezing gate, and the two-mode sum gate. So this is a universal Gaussian gate set. If you operate in the GKP encoded subspace, then the complete Clifford gate set is also comprising of these Gaussian gates, a rotation gate, or a certain rotation gate, a certain displacement gate, a shear gate, which is a combination of a squeeze gate and a rotation gate, as well as a two-mode control set gate. Okay, so this will not make our quantum computer universal because we need to go into the non-Gaussian regime to make it universal. So we need to implement also a non-Gaussian or non-Clifford gate for universality. So one approach is to use a cubic phase gate. This is a non-Gaussian gate that makes the setup gate universal. But it does not work that well when you're using DKP encoded qubits, which we wrote a manuscript about that you can find on the archive. So when you want to use DKP qubits in your quantum computer, then a cubic phase gate is not a good option for a non-Gaussian gate. However, we also know, as reported by Ben in this PRL paper from last year, that that if you work in the DKP encoded subspace, then a non-Clifford operation can be realized by Gaussian transformations, given that you have DKP and stillers at your disposal. So if you have DKP states, magic states at your disposal, then you can actually implement the non-Clifford operation using Gaussian transformation. So therefore, we will be focusing on implementing this only Gaussian transformations in our computing platform. Okay, so how do we implement these gates? I mean, for example, the squeezing gate and the sum gate, which are the most difficult gates to implement, Gaussian gates. So a squeezing gate, I mean, it doesn't look that difficult on paper because you just inject your state, could be the GKP state, into your squeezing device, which often is a parametric down conversion device placed inside an optical cavity. And then you squeeze your state, and this is then a squeezing gate. However, this does not work that well because it's difficult to inject your fragile quantum information into a cavity or into a squeezing device. You can do the same with the sum gate, but here we actually have the same issue. I mean, in the sum gate, this is basically just a two-mode squeezer, or it's a squeezing operator with a different phase matching conditions. So then you can realize the two-mode squeezing transformation, which is a sum gate. But here we we're left with the same complexity of injecting states into a squeezing cavity, and also it does not scale these systems. So many years ago, we looked into using offline squeezing resources for realizing squeezing gates and some gates. So you actually don't have to inject your squeezer or your state into your squeezer, but you can just have your squeezer as an offline resource and mix it on a beam splitter and perform a measurement, and then the measurement is effectuating the squeezing operation. And you can do exactly the same for the sum gate. So through measurements, you are effectuating the two-mode, the squeezing transformation of the sum gate. And this was demonstrated in the group of Akira Furukawa in those two papers. Okay, and this brings me to the cluster state approach. So these experiments here or ideas somehow hints that using a resource, an entangled or squeeze-like resource, you will be able to perform gates through measurements. And this is actually the idea of measurement-based quantum computing or cluster state quantum computing, put forward by Rausendorf and Brickel in 2001, and also for the continuous variable approach by Mengucci et al. So here the idea is to perform computation through measurements of in a multipartite entangled states. So more specifically, so quantum information processing is realized by teleporting the gates through this cluster. So for example, if your input state comes here from the right-hand side, then you teleport this input state into your cluster and thereby implementing a gate, for example, a single mode gate. Then you make a new teleportation to make a new gate, and so on and so forth. So this is just a teleportation circuit, just to remind you. So you have to start out by making entangled states, which you can do, for example, by interfering two squeeze states in a sum gate or on a beam splitter. And this is your resource for teleporting your input state to an output state. And then the settings of your measurement in the Bell measurement or the quadrature measurement determines what unitary transformation or gate you implement onto your input state. And this is the basic idea in cluster state quantum computing, that you do this teleportation circuits throughout your cluster. Okay, this is just another illustration of it. If you have a 1D cluster state, you have an input state, you perform measurements on the line of your cluster state to get an output state that has now been transformed according to your measurements. So it's fully programmable in the measurement settings of your quadrature measurements. Okay, so how do we build these cluster states? So I mean, as I already mentioned in the previous slide, we can make a super simple two-node cluster state just by interfering two squeezed states on a beam splitter. Or if you want to make it a bit more complicated, you can take 4 squeezed beams on 3 beam splitters. That will give you a square cluster state. But this, of course, does not scale to do it like this. I mean, there was experiments like this almost 10 years ago, where you just used a number of individually squeeze-like sources, interfered them in a beam splitter network array in order to get produce different types of cluster states. And this is one particular experiment from the group of Kunji Pang in China, where they used 8 squeezed beams to produce an 8-mode 1D cluster state. But this does not scale. And then there has been these quite interesting proposals on how to scale up the construction of cluster states. So you can use frequency multiplexing, something that was put forward by the group of Oliver Pfister many years ago, and tested 6 years ago, where they managed to produce a 60-mode entangled in a 1D cluster state. And similar approaches has been tested in the group of Nicolas Traps, where he used a comb of pump modes in order to generate a reconfigurable cluster state. The group of Akira Furukawa came up with this idea, or together with Mengucci came up with the idea of using temporal multiplexing, or temporal encoding, in order to make a very long a 1D cluster state, up to 1 million mode entangle on the line. So it's still a 1D cluster state. And actually, Akira Furukawa recently used this 1D cluster state to implement single mode gates, which Akira might want to talk about tomorrow when he gives the talk. So the problem here is that these are 1D cluster states, so they're not universal. So you can make single mode gates in this 1D cluster state, but you cannot make 2 mode gates. So therefore, you need to go to 2-dimension. And we came up with this idea for producing a 2D cluster state, which is universal for computation. So here the idea, so again, we use a temporal encoding, similar to what was done in the group of Akira from Tokyo University. So if we start from the right, we launch 2 squeeze beams produced from 2 different optical parametric oscillators into a fiber network. So this is what is done here. So we have 2 squeeze beams. The graph states are represented below. So just individual dots, they're separable states because they're not yet entangled. But then after the first beam splitter, we entangle pairs of nodes, thereby generating 2 mode squeeze states. So we delay one of the arms with respect to the other one with a distance that is equal to the distance between consecutive pulses. And then we interfere them again to make new links or new edges in our cluster state, and thereby producing a 1D cluster state similar to what was done at Tokyo University. And then we furthermore delayed, or we had another interferometer, highly asymmetric interferometer, where one arm was delayed by n times tau, where n in our experiment was set to 12. And this actually effectuated this roll up or coiling up of the 1D cluster state into a cylinder. And then after this coiling up, we had another beam splitter to make even new links, and thereby ending up with this 2D cluster state. Just some numbers. So the entire experiment was done at the telecom wavelength, and therefore we could do most of it in a fiber. So the only thing that was not in a fiber was the squeeze-like generator. The rest was performed in fibers. So the delays were 50 meters and 600 meters, and the tau delay here corresponds to the 50 meters corresponds to 250 nanoseconds, and we chose n, the second delay here, to be 12, meaning that we have 12 nodes on the circumference of our 2D cluster state. Okay, so a similar experiment was performed at Tokyo University, where they used a setup that was a bit more complicated because, I mean, they needed 4 squeeze beams, whereas we only used 2 squeeze beams, but the outcome is basically the same. So they also produced a two-dimensional cluster state, and the performance of these 2 cluster states are almost the same. So we compared these 2 schemes in this paper that you might want to look up. So here we compared the performance of the 2 cluster states, the one made from our group and the one made from Tokyo University, and they perform almost the same. Okay, so now we want to do computation, or we want to implement gates in our 2D cluster state. How do we do this? I mean, it has to be a combination of controlling the hardware and the software. So it is reconfigurable and is programmable, as shown here. So you start by, it consists basically of 4 different layers. So you start by deciding what circuit you want to implement, and then you resolve this circuit into different gates, different Gaussian gates, and then you figure out what phases do you have to change in your measurement quadrature, or what quadrature measurement do you have to perform in the hardware. And we have to keep in mind that the measurements are performed around the cylinder. So for example, we perform measurement of these 2 nodes, and then after this measurement, we will be performing of these 2 nodes. So we're performing measurement around the cylinder. This is the only solution we have. But it doesn't matter in what order we're performing the measurement. It does not matter because it's only Gaussian transformations. So the input states will be encoded onto the circumference, and the actual computation or the teleportation of gate will be performed along the cylinder. So we perform the actual computation orthogonal to the way we are measuring the state. So we are measuring the nodes around the cylinder, but the computation is actually performed along the cylinder. But I mean, in order to prepare for the implementation of for example,
Ulrik, you have 5 minutes.
5 minutes? Okay, thank you.
Yes.
Yeah. Okay, so we need to project out single wires, and this is done. So here we have a projection of the surface of the cylinder. So this is the circumference that goes down here, starting from -1. These are the mode numbers: -1, 0, +1, and so on and so forth. And now we want to do the computation orthogonal to this direction, so along the cylinder. And for this, we need to project out wires along which we can perform the computation. And this we do by performing measurement of these nodes here with a certain phase, pi/4, plus or minus pi/4, and thereby we are decoupling these nodes from the nodes on which we want to perform the computation. So we simply do wire projection, and we end up with these single wires here, along which we can perform computation. Because I mean, there are 12 nodes along the circumference, we can make 6 wires. So we prepare 6 wires, and this is also illustrated here. So here we are carving out our single wires in our cluster state through these measurements. And now having these single wires, we can perform teleportations along the wire and thereby implement the single mode gates. We can do the same for the 2 mode gates, but here we have to entangle pairs of neighboring wires, which is done by performing different type of measurements at these particular nodes where we are coupling the 2 wires. So this is somewhat the preparation for implementing single 2 mode gates, namely to project out these single wires or the coupled, as you see here, wires to prepare for single mode gates and 2 mode gates. Okay. So now considering the single mode wire again for implementing a single mode gates. So the teleportation that we perform along the wire is illustrated here. So we have an input state which is measured in a bell measurement together with 1/2 of an entangled state, and thereby we're teleporting the input state to the output state. And the transformation we perform is the one that you see here. So it corresponds to a rotation, a squeezing transformation, and another rotation transformation. And the angles here are just directly determined by the measurement angle or the measurement basis of our bell measurement or of our homodyne detector. And therefore we can now just choose these phases as we like, and thereby implement different gates. So if we choose the phases to be like this, then we implement a rotation gate. If we choose the phases like this, we implement a shear gate. And if we choose to be like this, then we implement a squeezing gate. So we can just choose any gate, or we choose any phase and thereby implement any gate. So the results on the single mode gates are shown here. So we have this expression for the quadratures, how the quadratures are transformed in the gate transformation. So we have input quadrature and we have the output quadrature that are transformed due to the gate. So this is a matrix representing the gate transformation. But then in addition, we have noise added. This is the second term, and the third term is a just displacement term that can be compensated for later on. So this we don't have to care about the displacement term. We have to care about, of course, the gate transformation as well as the gate noise. So we measure this matrix, this eclectic matrix representing the different gate transformation, the rotation gate, the shear gate, as well as the squeezing gate. And this is here are the results, where every single graph represent the entries of these unitary matrices of the different gates. And we see it fits pretty well the theory. We also did measurements of the noise. So this is the second term here that we are evaluating. And here we see the gate noise as both for the rotation gate, the shear gate, as well as the squeezing gate. And we inevitably will add noise in the computation because we only have finite amount of squeezing. We measure the noise that we expect to measure based on the initial squeezing of our states. We can also implement 2-mode gates. Here we have to project into a 10-mode cluster state, as you saw on the previous slide, and we have to select measurement basis for 10 different measurements, measuring 10 different nodes, and this is effectuating a control set gate. And here are the measurement results for the 2-mode gate. So again, we characterize the unitary transformation matrix of the control C gate or the sum gate, and we get a very good agreement with theory. We also evaluate the gate noise and get a good agreement with what we expect to get. Finally, we also realized the circuit. So this circuit consists of 12 different gates. So 2-mode gates and 10 single-mode gates. So we have 3 input states to our platform, and then we implement a 2-mode gate, a Fourier gate, another 2-mode gate, and a Fourier gate again. And we evaluate the transformation matrix, got good agreement, and also the gate noise was evaluated. Okay, I'm just rounding up now. So this was the task list for CV quantum computing. As I mentioned in the beginning, we have been addressing the 2 middle ones. So we have realized a fully deterministic and programmable multimode computing platform for measurement-based quantum computing. So the next step is to generate the optical GKP states with high squeezing. It's not an easy task, but this will be a crucial task. And also to implement quantum error correction, which is actually relatively simple in optics once you have the GKP states. And also you need to think about how to perform Qubit error correction in the system, for example, using surface codes. Okay, so I should definitely thank Mikkel Larsen, who did most of the work I have presented here, but also he was supported by Shushi, Kasper, Jonas, and also Jacob did a lot of work on GKP state encoding. You can look up many of his manuscripts on the archive. And then finally, I should also thank the rest of the group, and in particular support from all our foundations, in particular the support from the Danish National Research Foundation supporting our Center for Macroscopic Quantum States. Then I think I'll stop here. Thank you so much.
Thank you, Ulrik. So I forgot to remind you that you can ask your questions on the chat, but maybe I'll open with one question. Actually, we don't have much time either. So I was wondering about the protocol to generate the 2D cluster state. So if I understand correctly, so n in this delay time is basically, if you want to, for example, have a surface code, is going to be basically the length of the size of the surface, right? The size of the surface code. Am I right? This n tau.
Yeah. So n, exactly. So I mean n determines the diameter of the cylinder here, and the diameter is important. I mean, the bigger the diameter, the more input state you can have to your quantum computer.
Yeah. So I was wondering whether in the optics of having a fault tolerance threshold, the fact that the length, the duration of preparation increases with the size of the surface code, isn't it going to be a problem for?
Yes, of course, this will be a problem. So I mean, here we are using 600 meter. This is not introducing much loss, but at one point, I mean, if it becomes longer, I mean, then you will face loss. So the alternative is to increase the bandwidth of our optical parametric oscillator that will narrow the pulses that we are producing, and then the delay can be shorter. So it is, I mean, in principle, possible to produce thousands of modes along the circumference if you use a broadband optical parametric oscillator.
Thank you. So I have another question from Ben Rajala. So what schemes are you exploring for optical GKP state preparation?
Yeah, so I mean, currently we don't have any experiments on generating optical GKP states, but the the simplest approach, I believe, is a probabilistic approach where you combine squeeze states in a linear network, and then you project out the DKP state by measuring some of the modes at the output of the interferometer. So this is probably the simplest strategy, but it's also probabilistic.
Well, thank you very much. I believe there is no more question on the chat room. So I remind you that you have the possibility of asking your more questions on the Slack channel of the workshop. You have the link on the top of the chat list. So thanks, Ulrik, again for this very nice talk, and we can switch